Thank you for the invitation. My name is Chao-Lin Kuo of Stanford University. Um, Today I'm going to talk about Axion, in particular QCD Axion hunting with a novel type of large volume cavity. I'll explain what that means in a bit later. So I have the image of what the cavity might look like. It's a bit hard to unsee it after you see it once. And here I am in an outfit at the South Pole. This is for a London line of research that I'm doing, and it's measurement of B-mode polarization in the cosmic microwave background. So the designs that I'll be talking about have been published in two papers in JCAT. All right, so this is the allowed parameter space for QCD axions to be dark matter. So the x-axis is the Hubble scale of inflation, or equivalently, the energy scale of inflation. And the vertical scale is the axion mass. Okay, so it's a high mass going down, and it's also large scale inflation going to the right of the plot. This is a figure from Graham and Shirless two years ago. In that paper, they particularly emphasized the so-called stochastic window at the low mass range of Axion, also corresponding to low energy inflation. So the subject that I'm talking about today focuses on this, what they call classical window. So that's this sliver of parameter space out here. Um, it points to a very constrained parameter space that can still allow axions to be 100% of the observed dark matter density. So this is called the classical window or post-inflationary generation scenario for axions. There's quite a bit of interest in this window in the last few years because this involves cosmic defect strings, the precise energy or mass of axion is unknown, although conceptually, because we know the density of dark matter quite well, it's a one-to-one relationship. In other words, so this mass conceptually is completely determined. However, there is some modeling uncertainty, and I've listed papers predicting what that line, very little line, would be. And as you can see, there's still about an order of magnitude uncertainty in the precise mass of that axion. So that corresponds to about roughly 5 to 30 gigahertz or centimeter wavelength in the microwave. So on the right-hand side of this constraint comes from the measurement of my other line of research, the measurement of B-mode polarization to constrain the inflationary energy scale. So right now, the best limit, as you know, comes from Bicep, Keck, and Planck. And I can just tell you in a few months, this limit will be updated again by our group. So you can ask, look at all these possibilities. Why am I focused on this island of opportunity? Well, I think if you think about it, this post-inflation scenario is very tightly constrained. There's no fudge factor. Like I said, the only unknown parameter is the density of dark matter, which is measured now to better than percent level, a few percent level. And this simple model explains all of the high energy experimental data, as well as all of the cosmology and astrophysics. It's pretty remarkable that this tightly constrained, no fudge factor model agrees with the experimental data that well. So I think that deserves 2 exclamation marks here. So this is classical stuff. So it's been known for decades that axions, QCD axions, coupled to classical ENM through a few extra terms in an extended Maxwell equation, because we expect the Axion field to be highly coherent in the laboratory scale, on the laboratory scale. So this gradient A term will be negligible. Okay, so the dominant term, as many of you know, comes from this A dot B term. It generates an effective AC current, if you will, because it's in place of current density in Maxwell's equation, and it's in the direction of external magnetic field. So in an experimental setup, this B field will be large because you want to enhance the signal, and A dot is just what's given by supposedly QCD dark matter, and it generates a effective AC current, and it's going to be measured as if it's an AC current that comes from nowhere. So to take advantage of that effect, so this Axion haloscope idea was developed in the 1980s. So like I said, this is all decade-old stuff. And a cavity-based Axion haloscope looks like this. So there's a cylindrical cavity. The resonant frequency of that cavity can be tuned mechanically, and it's sitting in a intense, usually um, magnetic field generated by the solenoid in one direction. For simplicity and for the strength of magnetic field you need it to have a big effect. And in the end, so this coupling generates a line basically showing up as an additional signal from this conversion of Axion to photons to a cavity mode. So what you're looking for is a E dot B term. So B is the external magnetic field, the large quantity, and E is the E field, the ACE field of the electromagnetic resonance in the cavity. Okay, what you're doing is you tune by moving something in the cavity so that the resonant frequency shifts, and then you look for enhancement of signal. So this works very much like a radio. So you tune it until you hit external signal, or discover the external signal. So there are two, there are more than two, but in the US, there are two Axion haloscopes exactly using that concept. One has been 20 years old. It's called AMX. So because the frequency they're searching for, it's a very large cavity, meter scale cavity sitting in the intense magnetic field, 8 Tesla or something. And its little cousin haystack trying to go to higher frequency. So the whole thing is basically scaled down by a factor of a few in all directions. So the detectors, like I said, are these cylindrical cavities here for EMX, about a meter tall, and this one tens of centimeters tall for haystack. Okay, so exact same principle, using dilution refrigerators to reduce thermal radiation, using quantum detectors to reduce thermal noise generated from the cavity, and you just tune it, changing the resonant frequency. So, so this is like a similar plot. Axial mass in the x-axis now, and vertical axis is the coupling strength. Okay, so the cavity-based haloscope occupies this region. Okay, this region about 1 gigahertz, and for the stochastic low mass Axion scenario, there are there are a lot of different concepts being proposed to search for that. So I saw there was a talk on this Axion Virtual Institute about a heterodyne cavity idea. There's the lump element search, for example, the dark matter radio, the DM radio concept. There is a concept that uses NMR to search low mass. So a lot of people thought, high mass is just done deal. It's cavity based. Although there's a kind of a big issue here. So if you notice, this sensitivity line sharply goes up faster than the strength of QCD. Yeah, it's a function of frequency. Okay, so this is all log scale. So this actually is worse than it looks. Okay, and this is just from the frequency scaling from cavities. So as you go to higher frequency, the wavelength shrinks proportionally. The volume goes as nu to the -3 minus third power, and that happened to, and the scan rate is proportional to that volume square. So the scan rate is proportional to frequency to the -6th power. Okay, so it's a pretty serious problem. And in fact, the scan rate for Axion heliscope goes down very quickly, just about 2-3 gigahertz. Okay, so this is a very serious problem. So if you look at the scan rate, so like I said, it's proportional to volume square. It's proportional to Q factor, the quality factor cavity, linear order, and it's proportional to magnetic field strength to the 4th power. Okay, so in the order of importance, it's magnetic field, volume, and quality factor. So I inserted a little coefficient here, so that's what we call form factor that measures the essentially E dot B. Okay, and E being the electromagnetic field of the cavity, B being the external magnetic field. So that measures the volume filling efficiency of that particular mode. So we're looking for a mode that has to oscillate in unison, basically. Okay, so you can't just say, okay, I want to go to larger volume, so I have a giant cavity, and I'm just looking for higher order modes. That doesn't work because all those higher order modes oscillate like this. They have phases in the opposite direction, and as they oscillate, this form factor get canceled, and there will be none left when you go to very high order. So you can't just naively increase the volume of the cavity. That just doesn't work. Okay, so a very recognized future direction of Axion haloscopes, especially for high frequency, is to use quantum detectors. This is the standard recognized US approach, okay, to high frequency, higher than a few gigahertz. So there's a lot of promise in quantum detectors. There's a lot of funding for quantum detectors, and this is the approach discussed a lot in the US from lab and these places. And the idea is to use quantum detectors to lower the contribution from the thermal background. Okay, so I'm not going to talk about that other than pointing out the idea described in my paper is very complementary to that effort because, I'm working on this side of things to increase the input signal, try to increase the input, and here they're working on lowering the noise. So how does this work? So like I said, you can't just increase the volume of cavity blindly and look for higher order modes. So just a little bit of training for your brain. So how these electromagnetic modes work. So for a rectangular cavity depicted here. So as you know, the eigenmodes, they all look like sines and cosines, right? And essentially the eigenmode we're looking for corresponds to a frequency, which is the quadrature sum of wave numbers in all 3 dimensions. Okay, so this is the result of electromagnetism, basically. So the formula is given here. So as a result, as you change the dimensions of the three axes, you can you can get to a different resonant frequency. Okay, and there are 3 quantum numbers to describe the resonant frequency, as you all know. So in particular, if you imagine squeezing one dimension and extend 2 other dimensions, pretty quickly, one quantum number dominates because of this quadrature formula. Okay, and the wavelength of that resonant mode is dominated by one quantum number over the other, of course. So this is the plane wave solution. So in a plane wave, the wavelength is just the wavelength measured in one dimension, and the other dimensions are infinite basically, so are highly extended. So you can imagine doing that and then roll up that cavity into a circle. Okay, then that conceptually, that resonant mode will be oscillating again in unison, exactly what you wanted. So polarized this way and then polarized that way, polarized this way, polarized that way. And when it's coupled to an external magnetic field, it becomes a oscillating virtual current that can enhance emission in this particular cavity mode. So exactly the classical haloscope. So already this is a more compact geometry that has more volume, okay? And indeed, so that guess turned out to be true because this cavity, this ring-like cavity actually has an analytic solution. If you remember your graduate school E&M, this is just the linear superposition of Bessel function of the first kind and the second kind. The first kind acts like a cosine, the second kind sine. You're just matching the phase to match up the boundary condition. So indeed, there is a lot of E dot B. E is that E field. B is the external magnetic field. Okay, so that turned out to be true. I was very surprised that nobody recognized this in the. And then you can go further. So for scale, this will be the conventional haystack cavity, and its tuning rod at the center. Already, this looks a lot like shell solution I was describing, but the volume of this is of course many times larger than this. And remember, the scan rate is proportional to the volume square, and you can go crazy, and you can guess that if you do something like this, you know, you have a space filling or volume filling cavity, thin shell cavity, it probably will have that same mode, same eigenmode, because you can just think of this as a plane wave bouncing back and forth between the two walls. Okay, so the two lines here, one is the inner wall, one is the outer wall, and you can imagine doing, you know, this thing, fill the volume. Okay, and the whole thing, the volume of this cavity will be much larger than lambda cube, and the polarization is all in one direction as you want, and it will have very high coupling constant to external magnetic field. So this was described by in my first paper, and of course, you know, the community was, you know, really, I mean, would this actually work? How are you going to tune this, right? And indeed, you know, I was struggling for a few months on how you can tune this in a shell cavity. You can probably tune it just by displacing the center wall, just like how Haystack and ADMX tune their cavity. They tune it by turning an off-axis tuning rod at the center, but effectively they're displacing laterally the position of that tuning rod. And we can definitely do the same for the shell cavity. It's not very efficient. You're going to lose a lot of volume when you do that. And for this brain cavity, you know, it seems hopeless. Okay. Then I went to Starbucks and I realized, you know, you could tune the volume of that shell pretty uniformly um, if you have a little slope in the vertical direction. So again, it's a little hard to unsee this once you've seen it, but I was surprised that nobody proposed this geometry um, up to now. So you can see the distance between the inner wall and outer wall, written as W here, changes manifestly, uniformly, as you move the inner cone vertically. Okay, and because you know you're looking for a very small cone half angle alpha here, one expect a very large cosine factor, um, or nearly unity, or very little loss in sensitivity. So to realize this, there has to be a gap in the inner wall and outer wall. When you have a gap, the mode leaks out, and you're not going to have a high Q cavity anymore. But the way to solve that is standard in, my day job as a cosmic microwave background person. So you have corrugated structures to damp out the field at the boundary. I have these what we call quarter wavelength corrugations to manage the E field. So the E field drops to nearly zero at the boundary anyway, so it won't leak out from the tuning, which is 1/10 of a wavelength. So with this, you get 20% tuning range. Okay. So this, and then of course there's a solenoid field to provide the magnetic field. So I took exactly this and ran numerical solutions to get the electromagnetic eigenmodes to calculate the form factor, to calculate the total volume. But that is still not missing a lot of volume, right? So imagine you have a solenoid, okay, and you just have no cavity in the center. So ideally, you want to go to the brain design again, and for that, you can start out with the general meandering curve like this. See one here in orange, and then you kind of extrude it, okay, to form a cone, a large cone, like here, and you take the lower half, the skinny part of that as the inner cavity, inner wall, and the upper part as the outer cavity. And all of a sudden, you have a generalized cone. It almost fills the entire space, and it can be tuned symmetrically in the sense that as you tune the entire space, that defines the frequency of the resonance changes uniformly. Okay. So once again, you can get 20% tuning range if you do this following this recipe. Okay. So that's really the gist of the idea. And then because of the pandemic shutdown, I had a lot of time to create these solid models and to feed them through 3D FEA packages. And indeed, these are the solutions I got. So the arrows represent the direction of electric field, and the color, the grayscale, represents the strength of that. And indeed, you have a volume filling mode whose frequency is determined by the distance, and yet it fills a much larger volume. And that's precisely what you want in Axion experiment. I'm running low on time, but here's the result of all of that calculation done over 6 months of shutdown basically, and each point takes a lot of time to run. You can see the effective volume, or the form factor times the volume of these new cavities exceed conventional cavity by orders of magnitude. We're talking about non-trivial orders of magnitude, not a factor 2, not a factor 5, orders of magnitude improvement in scan rate if these cavities can be built. So I'm wrapping up. So can this, be extended to more than 10 gigahertz? So we know they have problems at 5 already, but can this cover the entire possible post-inflation scenario, which goes up to 30, 40 gigahertz, depending on who you talk to? One can imagine generating that generalized cone, okay, from a space-filling Hilbert curve, right? Okay, not everybody thinks that this can be built, but you could imagine a very precise 3D printing type fabrication technique. If you can design it, you just do exactly that, following that recipe, little displacement, and then take the top half and the second half, and the lower half to be the inner and outer wall of it. Okay? It's going to look very complicated. Again, nobody knows whether this can be built, but this is one concept. Another way of doing it is doing it more, conservatively. in one way, but more aggressive in the other. That's to have multiple cavities, and each one is this meander, and then you try to combine the signal from cavities. Um, and if you can build very large volume per cavity, you can reduce the number of total cavities whose signal you need to combine. And for each of these cavities, you need an individual tuning and alignment mechanism. So there are a few high frequency techniques. I don't have a lot of time to go into, but they are at a similar maturity stage, I would say, to these crazy sounding cavities. So one is the electric disc haloscope being pursued in Europe and Germany. You have a bunch of dielectric discs um, also under magnetic field to create the conversion signal. And a new concept is to use metal wires. This is the so-called plasma haloscope idea. Again, all of these new concepts are trying to cover this highish frequency range, perceived to be difficult. I believe these complicated cavities is among more promising. Okay, so that's what I prepared. If you have questions, ideas, please write to me. And I have received a lot of questions about these very non-conventional cavity designs regarding causality, fabrication, alignment, and I'd be happy to answer that. Again, these two papers, the first one is published, and the second one will appear in JCAP in a few weeks. I'll stop here.